So before we look at the reaction to form the epoxide, we need to consider why is MCPBA a good electrophile? And the answer is once it undergoes a reaction, you end up with a leaving group, and that leaving group is stabilized by some resonance structures. So let's look at the structure of MCPBA to start with. So we have this oxygen double bond, and we saw before with the peroxide that we know that that OO bond is actually weaker than you would think. Again, we explained why that was. They're both electronegative atoms, they're both sharing a pair of electrons, whereas actual fact they'd much prefer to form a bond with something which meant they get more of a share of the electrons within that bond. So if you then take a nucleophile, okay, what happens is it will attack one of the oxygens, and if we attack this one here, we can show how that can lead to other a good leaving group and good resonance structures. So we attack this oxygen here, we form a new bond between the nucleophile and the oxygen. That means the pair of electrons in the oxygen-oxygen double bond can be taken by the other oxygen in that system. So what we end up with is our nucleophile with an OH group plus our leaving group, and what we can see from here is that we can draw a resonance structure of that, which again what that shows is that the negative charge that's formed as part of the leaving group, that charge can actually be spread across multiple oxygen atoms, and therefore that stabilizes it due to that resonance structure. So once we understand that MCPBA can act as an electrophile, we can then look at how the reaction with the alkene might happen. So if we draw our alkene here, okay, and we have our MCPBA, we can look at this and think of it in a way as a form of the oxygen-oxygen bond is almost like a polarizable bond. So it's very similar to the BR-BR. So we can think, well, in that case, we know that we can react with one of those oxygens. So we can form this new bond here between a carbon and oxygen. Now, what you might think is that would, well, we could then break the oxygen-oxygen double bond, okay, around to here, and you could think that this would be a bit similar to, you know, we've added the oxygen here, and we would end up with a carbocation. Now, in reality, that carbocation never really appears. Okay, so this is not quite what happens. All of this happens in one step as a concerted mechanism. So we break open the oxygen-oxygen double bond, we form a new oxygen-carbon double bond here, and then the electrons in this carbon-oxygen double bond here will actually form a new bond between the oxygen and the hydrogen, and then finally the electrons in the hydrogen-oxygen bond will go on to react with what is now, you know, it's not a carbocation, but it would be an electron deficient region. So what this goes to give us is our epoxide. Now, of course, at the start of this, we had some R groups. They were both on the same side of the molecule, and by doing this reaction, we have ended up with some stereocenters. So doesn't matter which face it attacks from, the R groups will end up both pointing in the same direction, and we would also end up with the hydrogens that we didn't show in the first product pointing in the same face, same direction as well. And then we would end up with this species afterwards. And so because all of this happens at the same time, there is no opportunity for bonds to rotate. That's why we end up with, if we have some stereochemical information in the starting material, so for example the cis alkene, we will end up with what's called a cis epoxide, and equally if you have a trans alkene, you would end up with a trans epoxide. Now, on the previous slide with the use of MCPBA, the side product that we formed, if you remember, we formed this this side product here. Okay, you can see that this is a type of carboxylic acid, so it's got this acidic byproduct. Now, sometimes that's fine, but other times that would be a problem. So we can use alternative reagents which avoid this problem. So if we go back to our test alkene, we can use something called DMDO, or dimethyl dioxirane. Okay, and that is a very strained three-membered ring with the two oxygen atoms, and we can imagine the same thing happening. That oxygen-oxygen bond is polarizable, so we can react with one of those oxygen molecules. The oxygen-oxygen double bond, single bond would break, and we would form a new oxygen-carbon bond, and then we would be able to take the oxygen, the electrons out of the other carbon oxygen bond here and react them with the other carbon atom. So very similar to the MCPBA example. So we would then end up with, once again, our epoxide, and remember we still have that stereochemical information because everything has been done, all the bonds have been made and broken at the same time, and what we end up with as our side product is acetone, so a very simple ketone molecule which isn't going to be acidic, so isn't going to cause any problems in later reactions.